All right, let's have an introduction to lab statistics. One of the most important things in labs is data. And in order to work with data, we have to have a way of evaluating it and summarizing it. And that's where statistics comes in. Statistics also provides a convenient method of drawing conclusions and making points about our data. Or, in the words of Mark Twain, it's a convenient way to lie about our data. After all, in his words, there are lies, damn lies, and statistics. So let's get ready to lie like Jim Carrey. The first statistical concept that we want to talk about is one you're probably already familiar with, and that is the concept of an average. The average, represented by the variable x with a line over it, is the sum of a set of numbers divided by the sum of a set of data. Let's actually do that. Is the sum of a set of data divided by the number of data points in the set. Now, if we wanted to be super fancy, we could say that the average is the sum of x's from I equals 1 to I equals n divided by n. However, unless you've had set notation or some really advanced math, that's garbledygook and me just really enjoying drawing that Greek sum symbol. To put it in more convenient parlance for us, the average is the sum of a set of numbers divided by the number of numbers in the set. Let's take a look at a quick example that we could probably all be familiar with. In fact, why don't you write down Dr. Phlox? Write down Dr. Phlox. Dr. Phlox from Enterprise. Dr. Phlox, and that's with a PH. All right, let's move on. Let's take a look at our example. I gave a quiz in class the other day. And I have 11 students in my class, and their quiz grades out of 12 were as follows. Let me make sure I put 11 up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yay, I can count. All right, so I have 11 students in my class, and these were their quiz grades. If I want to figure out the average quiz grade for the class, what would it be? Okay, well, let's take a look. The first thing we would do is we would add up our scores. So I'm going to add, come on, 12 plus 12 plus 12. I'm going to add all my quiz scores together. 8 plus 8 plus 10 plus 8 plus 8 plus 12 plus 8 plus 12. And when I do that, that gives me 110. So I've added up all my quiz grades. Then I'm going to divide by my number of students. So I've got my sum of my data here, and my number of data points there. And when I punch that into my calculator, 110 divided by 11, that gives me an average of 10. So my class average was 10. Notice that there's a little bit of a problem with the average here. Even though the class scored an average of 10, how many people in the class actually scored a 10 on their quiz? Only one, yes? So while we could say, and we could represent this set of data as an average of 10, it may not give us the best picture of this set of data. Which brings us to the need for more statistics. Is saying the class scored an average of 10 on the quiz a good representation of their scores? Well, no, it's not, right? And it is at the same time. If we looked at this data, only one person actually scored a 10. However, about half of the students scored above that 10, and about half of the students scored below. So in a way, it's a good representation of the data, but it doesn't really give us the full picture. That leads us to another important statistic, a statistic that helps us represent how spread out a set of data is. The average kind of represents the midpoint of the data. We're wanting to represent how spread out it is now. To do that, and that statistical indicator is standard deviation. Standard deviation is a hard thing to really put into words. How I like to describe it is standard deviation represents, on average, how close measurements average, how close data points are to the mean or average of a set of data. Mathematically, standard deviation looks really, really impressive. Standard deviation, and I'm going to represent standard deviation since they didn't give another variable to use here. In your lab manual, I'm going to use SD for standard deviation. Standard deviation equals the sum of every data point subtracted from the average and squared divided by the number of data points divided by the number of data points, then taking the square root. Now, a couple quick notes. Your textbook uses for the standard deviation that you divide by the number of data points. Most other things have you divide not by your number of data points, but your number of data points minus 1. So you do see a little bit of a disagreement in your book there between what is the standard practice out there. Just a heads up. Now, standard deviation seems really, really bad. Let's make this look a little bit easier. Let's go back to our quiz set and see if we can't figure out the standard deviation of our class on the quiz. Grades up there, and while I'm throwing the quiz grades up there, why don't you write down to Paul? Everybody write down to Paul. Quiz grades for 11 students. I know, it's not the same order as it was on the last time I presented it to you, but it's still 12 students scoring 5, still 12 students scoring 8, and still 5 students scoring 12, 5 students scoring 8, and 1 student scoring 10. The exact same as last time. And we already determined that the average score on the exam was 10. In order to find the square root, we're going to in order to find the standard deviation, we're going to solve for the standard deviation in a couple steps. So let's write standard deviation in terms of steps. So standard deviation steps. Calculate the average. We already did that. Step 2. Subtract each number from the average. So let's take a look at doing that. All right. So our average is 10. 10 minus 12 is negative 2. 10 minus 12 is negative 2. 10 minus 12 is negative 2. 10 minus 8 is positive 2. 10 minus 8 is 10 minus 8 is 2. 10 minus 10 is 0. 10 minus 10 minus 8 is 2. 10 minus 8 is 2. 10 minus 12 is negative 2. 10 minus 12 is negative 2. 10 minus 8 is positive 2. So if you looked at that fancy formula on the other page, what we just did in this step is we did the subtraction of each measurement from the average. Now, step 3, square the difference. And I have to stress that you can't mix up these steps. You have to do these steps in the order that they're given. So we're going to square each difference. So we're going to go through and square each one of these individually. Now, because we're dealing with some false data, squaring here is going to be pretty simple. Four, 4, 4, 4, 4. Oh, 0 squared is 0. 4, 4, 4, 4, 4. So we've squared all our differences. Now we're going to do, and if you think about what we just did in the formula was we took our differences, took our average minus each measurement, and we squared it. Now step 4. Sum the differences. So I'm going to take 4 and add it to 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 4, add it to 0, add it to 4, 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 add them all up, and we add them all up, and we get a sum of 40. So what we've done here is, if we're in the formula now, we've now done this sum step. Now, here's where standard deviation formulas differ just a little bit. Based on what your textbook says, you're going to divide by your number of measurements. Or divide by your number of data points. In this case, we said we have 11 students, right? So we have 11 data sets. So we're going to take our 40 and divide by 11. So 40 divided by 11 equals 3.636 is what your calculator is giving you, home gamer. And we'll talk about sig figs with it later. But that's what you get when you divide 40 by 11. This actually has a special term. Well, let me get not too far ahead of myself. So what we've done in number 5 is we've taken the sum of the squares of our differences and divided by our number of data points. This quantity here, this 3.6, also is a statistical term. This was referred to as the variance of a set of data. So we would say that our quiz grades have a variance of 3.636. Now, to get standard deviation, which is what I prefer to use, we have one last step to do. Six, take the square root. We take the square root. So, square root 3.636, and that's going to give us, full disclosure at home gamers, I've kept the number from my last answer in my calculator, so I haven't taken it out, so you may get a little bit different than I'm getting. But I get, because it's a standard deviation, remember we don't know the sign, so it's going to be, I'm getting plus or minus 1.91. So my standard deviation would be 1.9, plus or minus 1.9. So for my quiz grades, I would say that I have an average of 10 and a standard deviation of plus or minus 1.9. Now, you'll notice that I'm writing that 9 below the line, which is my way of communicating with you that I don't consider that 9 significant. Why is that? Well, we only measured, or I only graded the tests to the ones place, yes? So can we really differ from a measurement in the tens place if we didn't measure it? No, we can't really. So if we wanted to give a lot of information, we could say 1.9 sub to let people know that 9 isn't significant, or I could say plus or minus 2. You can't have a standard deviation outside the range at which you've measured. So the last sig fig in your measurement here has to represent the first sig fig in your standard deviation. Standard deviation can go farther. We could have a standard deviation in the tens place here if we wanted to, but we can't go past that last sig fig there. So the best way to talk about this data set that we've given, if we wanted to characterize how the class did on the quiz, what I would say was that the class had an average of 10 plus or minus 2 points, meaning that the class had an average of 10, but most people scored somewhere between 12 and 8. And that's what your standard deviation does. It kind of helps you realize how large the set of data is spread around the average. When you graph a set of data, I'm going to shrink things down a little bit here because I'm going to want to come back to them, so I don't want to quite get rid of them yet. When you graph a set of data, where you put number of data points on this axis, and you put student score on this axis, in a typically normally distributed set of data, most people are going to score close to the average. And as the scores get farther away from the set of average, the number of people scoring it decreases. As a general rule, roughly 95% of your data is going to be within +3 standard deviations of the average or -3 standard deviations of the average. And when you hear people talk about the bell curve, that's what they're talking about. And they're talking about normally distributed data. And I came up with an artificial set that wasn't normally distributed because I only had one person score my average. Why don't you write down to Paul? Everybody write down to Paul. T''Pol, to Paul. Another thing I want to talk about real quickly when it comes to standard deviation data here. Stop that. Is let's rationalize why we did what we did in this formula. Why did we go through all the trouble when we calculated the standard deviation of squaring our differences from the average, and then at the end taking the square root? Here's why we did this. If we looked at our initial differences from the average here, our initial differences from the average, some of those differences are positive and some are negative. If we had added them all together without squaring them, we would have had a sum of 0, implying that all our data, all of our students scored the average, and that obviously isn't the case. So to deal with that positive negative difference from the average, we square them, resulting in all positive numbers. Then we sum them together, and then we take the square root to undo the effects of squaring them. And that's the logic behind your standard deviation formula. Let's make sure everybody's on the same page when it comes to standard deviation. What I'm going to do is I'm going to write an example, and I'm going to ask you to calculate the variance, the average, although not necessarily in the order I'm giving them, and the standard deviation for the following data. And Fe is the elemental symbol for iron, so I'm asking you to average and find the standard deviation for the mass of iron in an unknown rock. and 0.19 grams, and I'm going to need to make myself a little bit more room here. All right, so we've gone to the lab, we've conducted an experiment, and we've gotten the following masses of iron in an unknown rock. What I am encouraging you to do, and just for clarity's sake here, shoot, stop that. Ah! That's a 9, right? You can tell 0.19. All right. Pause me, work this, then come back and look at my answer. Do. Did you pause me? I told you to pause me. Please tell me you paused me. If you didn't pause me, I am disappointed in you, and the trust between us is forever gone. I don't know if we can repair the relationship. Seriously, I seriously hoped you paused me. Okay. So step 1 is we're going to calculate the average. And to do that, we're going to have to add up all the numbers in our data set here. And when I do that, I get 0.18 plus 0.18 plus 0.2 plus 0.2 plus 0.19 plus 0.19 plus 0.2 plus 0.18 equals when I sum them all together, I got 1.52. Then how many data points do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 data points. So 1.52 divided by 8 gives me an average of 0.19. Now, all your numbers will not work out this pretty. All right, so now we've got our average. Now let's get to work on that variance. Step 1 in calculating your standard deviation or your variance is to subtract each measurement from the average. So let's do that. The average minus x is what we're doing here. So 0.19 minus 0.18 equals 0.01, 0.19, 0.18, 0.1. 0.19 minus 0.20 equals negative 0.1. 0.19 minus 0.20 equals negative 0.01. 0.19 minus 0.19 equals 0. 0.19 minus 0.19 equals 0. 0.19 minus 0.19 equals negative 0.01. Gotta clean that up a little bit there. That got kind of messy. Matter of fact, it sounds nearly as messy as the person who keeps walking past my office on their cell phone, talking about their personal life really loudly so that I can hear about it. Ooh, sounds like they're having chicken for dinner tonight. All right. Now I got ahead of myself. See, I got distracted. Then our last one, and that would not have been good. Positive 0.01. All right, let me see. Do I have 1, 2, 3, 4, 5, 6, 7, 8? I've not skipped any data points, have I? Let's see. That matches to that, that matches to that, that matches to that, that matches to that, that to that, that to that, that to that. Okay, I subtracted all my points from the average. So I now have my differences. And my next step is going to be to, whoops, I can't delete that, can I? Right. My next task is going to be to square all of them. And 0.01 squared is shoot. I'm trying to write on top of my average now. That's no good. It's 1 times 10 to the negative fourth is what it is. So 1 times 10 to the negative fourth times 1 times 10 to the negative fourth times 1 times 10 to the negative fourth, 1 times 10 to the negative fourth. That's 0. That's 0 still. That's 1 times 10 to the negative fourth, 1 times 10 to the negative fourth. Then I'm going to add them all up. And what does that give me? 1, 2, 3, 4, 5, 6. 6 times 10 to the negative fourth is the sum of my squares. Now we're going to divide by our number of numbers. So divide by our number of numbers. In this case, we said we had 8 measurements. So 6 second EE negative 4 divided by 8. And that gives me 7.5 times 10 to the negative fifth. Oh, just so you'll know, 1 times 10 to the negative fourth, if I wrote it out long way, would be 1.1231, right? And that would be my 6 to the negative fourth, yes? So if you don't have your calculator in scientific notation mode, you should be seeing at this point 4 zeros in front of a 7 and then a 5. This is my variance. Variance is often represented with the Greek letter sigma, just FYI. So there's my variance. So I've got my average, I've got my variance. To get my standard deviation, I take the square root of my variance. So I'm going to take that variance, I'm going to take the square root of it. And that gives me (0.00866 plus or minus 0.0866. Plus or minus 0.009. We're always going to report at least one significant figure for our standard deviation, even though this one technically lies outside that boundary of our measurement. I don't want to leave the standard deviation unreported. And I don't want to make it overly complicated either for you. So there we go. Beep. Oh, I shouldn't have beeped. Would you mind writing down Malcolm? Write down Malcolm.